So my name is Luca Montanari. I'm a consultant, concrete consultant for Europe, and I'm currently pursuing a PhD at University of Texas at Austin. This work was performed while I was still working at FSW8, and the topic is basically how including accelerated admixtures inside our concrete mixture can affect the electrical resistivity of the cement mixture. This work was performed in collaboration with Professor Maria Younger and with Michelle Cooper, who is the federal lab manager for the concrete lab at Turner Fairbank Highway Research Center. This is just a disclaimer for government. This is us. And these are the acronyms you're going to see throughout the presentation. The ones that are in bold are the ones that I really want you to focus on. So we're going to be talking a lot about bulk resistivity, degree of hydration, formation factor, and pore solution resistivity. It's just general outline. So why are we performing this work? My general topic for my PhD thesis is repair materials, and specifically for full depth repairs, what we typically observe being used in the field are these high early strength concrete mixtures. And the way we design this concrete mixture is by having very high cement contents, very low water cement ratio, basically no SCMs, and very high dosages of accelerators and water reducing mixtures. And all of this is combined to try to generate as much PSIs as possible within just a few hours. You have to imagine that these mixtures can reach 4,000 PSI between 6 to 8 hours from initial mix. And why are we doing that? Because basically, at an agency level, we want to minimize the influence that we have on traffic. So we have to repair that section, but we don't want to disrupt the traffic in that area. So we're really trying to get to high strength as soon as possible. So what happens, though, is that once we started looking into the specifications of many DOTs, there's barely any quality control that's done on these mixtures. So we care about the strength, but we don't really care about anything else that happens to that mixture itself. And what some reports have highlighted is that because of the lack of interest in any other property, we see fairly early, premature failures in a lot of these sections that are being repaired. So we repair them, and then within a few years they fail again, and so we have to repair them again. So we started looking into how can we improve the way we test these mixtures. And one of the things we thought about is using electrical tests. Electrical tests are fairly rapid type of tests, and they give us very useful information on the transport properties of our concrete. And transport properties are important because they basically determine how much fluid the concrete absorbs and how fast ions can travel through the concrete. And we all know that durability of the concrete is influenced by things like freeze-thaw performance or by corrosion resistance. And we know that corrosion is driven by chloride ions or carbonation. And so these transport properties are important if we see that these mixtures are failing too early. And this slide kind of highlights the fact that, as I mentioned before, we include very high dosages of accelerated mixtures. And what typically happens is that in a normal concrete, we would have, in the pore solution, which is basically the solution that you find inside the pores of the concrete, we have sodium, we have potassium, we have sulfates, we have calcium. But once we start introducing these mixtures, we make the pore solution much more complicated in terms of chemical properties and in terms of electrical properties. So I've highlighted here the presence of chlorides in case of we're using chloride-based accelerators, nitrates, nitrites, and so on. So it was not trivial to just assume that these mixtures would be okay to test these mixtures with electrical tests, because once we start affecting the pore solution, we're going to ultimately affect also the bulk electrical properties. So resistivity is not just only affected by the pore solution properties. We have all these other factors that play a role into affecting the measurement of resistivity. And we have temperature, we have degree of saturation, we have the pore solution. But what we're really interested in is looking at the porosity and the conductivity, because those are going to be the two factors that drive our transport properties. So the research objectives for these were to look how these admixtures can affect the electrical properties, the degree of hydration, and the microstructural features, and verify whether electrical resistivity as a test can actually capture and the microstructural features of this type of concrete without being affected in one way or the other from the inclusion of accelerators. And again, this was important because we wanted to verify if we could use or not electrical tests for quality control and really include these type of tests into the mixture design for these applications. So these are the type of accelerators that we use during our study. You can see that the first one, for example, is a corrosion inhibitor, which I don't know if everybody knows, but it also acts as an accelerator. And there's a little bit of concentration information. So every one of these different admixtures has different chemical components, different recommended dosages. And what we typically adopted in this study was about 50% of the maximum allowed or the maximum recommended dosage for from the supplier for this particular admixture. So we're around, again, 50% of the maximum dosage. The way we cured the specimens for this test was in seal condition. We didn't want the lime water or the moisture to affect the pore solution in one way or another. And also, the other factor that made us choose this type of curing was the fact that based on a survey that was done among different DOTs, basically these type of repairs receive basically no curing. A lot of DOTs don't even apply a curing compound on the repair once it's cast. So seal condition was the type of curing that best replicated what was going on in the field. And I can here we basically show the temperature evolution, and you can see that every one of the admixture influences the temperature evolution in this type of curing a little bit different. One important factor that we consider in our analysis was the degree of hydration of the system. Every admixture is going to have a slightly different effect on the development of the hydration products and the rate of hydration. And so within the first 7 days, we relied on using isothermal calorimetry, where we basically measured the cumulative heat and we normalized it by the total reaction enthalpy, which was based on the chemical composition of the cement. And past 7 days, we relied more on the TGA, which basically measured the weight loss after ignition of your cement sample, cement hydrated sample, and then you normalize it by a reference total bound water, which represent the total amount of moisture that should be bound by the cement at full hydration. We extracted the pore solution from our sample. Again, we were trying to verify the effect of these admixtures on the pore solution, and it's not an easy task to perform. We had a jig at the FHWA labs that allow to do that, and then once the pore solution is extracted, we measure the resistivity using this small cell where you basically fill the solution. You fill the cylinder in the middle with the solution, you measure the impedance, and then you convert that into resistivity or conductivity based on the geometry of the cell itself. Because we wanted to verify if we could relate the resistivity to microstructural features, we actually tested the overall porosity of our systems. And to do that, we cut the paste specimens into pretty thin discs, about 5 millimeters thick, and then we vacuum saturate them. And once you vacuum saturate them and you have the weight at oven dry, you have the weight at full saturation, you can back calculate the total porosity of your paste. And finally, we actually measured the bulk resistivity. It's a very quick test. I recommend any lab that's working on durability to include one of these equipment in their lab, because it's a very reliable and repeatable test and can give you very interesting information about the mix. And the way we calculate formation factor, we normalize the bulk resistivity by the pore solution resistivity. So we extract the pore solution, we tested it, and we have the bulk resistivity from this test, and then we can get the formation factor by normalizing one by the other. So these are the results on the degree of hydration. As I mentioned, for the early ages, we relied on isothermal calorimetry, and for the later ages, we relied instead on TGA. You can see that there's a little bit of discrepancy at 1 day between TGA and isothermal calorimetry. Typically, TGA is not very recommended for such early ages, so that's why we relied on isothermal calorimetry for those. And these testing ages match the ages at which we tested the pore solution and the bulk resistivity. One important point to notice here is that every accelerators affects the degree of hydration a little bit different. So we expect accelerators to increase the degree of hydration at early ages because we want to gain strength fast, but that doesn't mean that at later ages the degree of hydration is still going to be higher. So some accelerators actually reduce the overall late age degree of hydration compared to the control system that you can see in the first column. So these are the pore solution results. One of the things that I think is mentioned in ASTM C1202, which is the RCPT ASTM, is that corrosion inhibitors, mixture with corrosion inhibitors should not be tested because the results are not reliable. We show here that actually the very early age, the pore solution is highly affected by the presence of admixtures, but over time that effect reduces by a lot. And admixtures that initially increase the conductivity of your solution, so reduce the resistivity, ultimately don't necessarily have the same effect over the long-term tests. So it was really interesting to see, for example, that you can see like the blue line is the calcium chloride admixture, accelerated admixtures. At the very early age, it decreases the resistivity, right? We're putting all these chlorides in the solution, we're dropping the resistivity, but over time, it actually has the opposite effect and actually increases the resistivity, and by 28 days, it's very close to the control. So at the very early ages, we notice up to 35% difference from the control, and then by the 28 days, that difference reduced to 20%, less than 20%. So these were promising results for us because we could show that actually, we typically perform quality control around 28 days or even further, and by that time, the influence of the accelerator seemed to diminish a lot, and so resistivity could actually be could potentially be applied to these mixtures. So this is the bulk resistivity measurements. We can see the control is always higher than the rest, although we saw before that maybe pore solution is not exactly the reason why the control is higher, because the effect of pore solution varies over time, and it's not necessarily reducing the resistivity. And once we correct for the degree of hydration, so we're not anymore thinking about days, but we're looking at the bound water or the total enthalpy of the system, we can see that the curves pretty much collapse. So we are altering the degree of hydration evolution over time, but once we account for that, there's not so much difference between the different systems. And this kind of tells us that some admixtures might change the microstructure evolution over time, but in general, the ones that we observed did not really have a major effect on the microstructural evolution. And here instead is the formation factor. So in the formation factor, we account for the pore solution resistivity, and it's got very similar trends compared to the bulk resistivity. So the control is always higher in terms of evolution over time. But again, once we account for the degree of hydration, not so much different except for like one single admixture. So all the accelerated admixtures, although they show different values based on time, the microstructural feature seems to be developing similarly as a function of degree of hydration. And finally, we looked at the porosity. And so we care again about the porosity because we want to make sure that our electrical test can represent microstructural features of our concrete even in presence of accelerated admixtures. And again, we have opposite trends, of course, because resistivity goes up over time because we're densifying the microstructure, and porosity is going to go down over time because we're reducing the overall porosity as the cement hydrates. And again, similar trends, but in the opposite direction. And again, once we account for degree of hydration, not so much difference among the different admixtures. And finally, this is the plot that I want you to remember. Basically, both bulk resistivity and both formation factor show very good correlation with the porosity that we measure on the system. So this was very important for us because it allows us to move forward with other tests and say, yes, okay, these electrical tests can actually tell us useful information that can be used in the quality control of our mixtures. It can be proposed to be included as quality control tests for highly strength concrete mixtures for repair applications. So a little bit of a summary here. So the degree of hydration, just because the accelerators increase the degree of hydration at early ages doesn't mean that they increase the degree of hydration at later ages. Some of them actually decrease it, and at 28 days, there was a drop up to 9% compared to the control without any admixtures. The pore solution effect is greater at the early ages. Over time, the effect of these admixtures lessens. The bulk resistivity, we can see the control is always higher compared to the ones that where we add admixtures that accelerate the reaction, but it's not only a factor that it's attributable to the pore solution. So in the current standard, there's a general thought that pore solution is the reason why we see these lower numbers when we perform electrical tests. This is not the case. Formation factors show similar trends to bulk resistivity. So there's been a lot of talk about bulk resistivity versus formation factor, what we should be using for quality control. They show similar trends in this case. And once we account for the degree of hydration, we see very limited effects of the admixtures at this dosage on the microstructural features of our cement paste. And the good news is that both bulk resistivity and formation factor have good correlation with the porosity. So they can tell us useful information on the quality of the transport properties or the microstructural features of the system in case we want to apply them for quality control in repair applications. So in conclusion, again, the effect of accelerated mixtures seems to lessen over time. So there's a lot of talk, for example, right now to extend the testing time from 28 days to 56 days or past that. So in case we did that for these type of mixtures, it could actually probably lessens the effects of these type of admixtures. We saw very good correlation between bulk resistivity and porosity, which is promising then to further studies on correlating these to transport properties. And again, the microstructure features that we measure were pretty well correlated with these test measurements. This is a reference of the paper that kind of includes all this information. You can find it on CCC from last year. And then before I'm done, I wanted just to advertise this event that's going to happen on March 11th to 14th of next year on the topic of data science for payments, and is organized by the FSWA. Thank you.